Imagine you are driving down the highway. You pass the police speed trap, and the radar gun clocks you at exactly 73 miles per hour.
Which is, just slightly over the limit, but entirely normal.
Right, the very specific normal speed. But then you get a ticket in the mail from a traffic camera that was located at the very start of your road trip. And its math insists that your speed, like factoring in your entire journey, was exactly 68 miles per hour.
Which is super confusing. I mean, normally you just assume one of the cameras needs recalibrating, right?
Exactly. But what if you check both cameras and they're working perfectly? Suddenly, you aren't just questioning your speedometer. You are questioning the very laws of physics that govern how cars even move.
Yeah, which is a pretty terrifying thought for a morning commute. But it is actually the exact situation modern astronomy finds itself in today, just, on a cosmic scale.
Welcome to the Deep Dive. Today, we are opening up your custom stack of astronomy research. You sent us this really fascinating pile of memos, a detailed study guide, and these breakthrough articles from astronomy and astrophysics, plus some context from space.com and Wikipedia.
It's a really great stack of sources.
It really is, and we are using it to look at the universe's ultimate speeding ticket. We are tackling the Hubble tension. Basically, our two absolute best methods for measuring the expansion of the universe are giving us completely different answers.
Yeah, and they won't budge.
Okay, let's unpack this. The universe is handing us this massive cosmic discrepancy, and scientists are they're basically arguing over the radar gun. So our mission today is to explore a brand new third way of measuring the cosmos that might just solve this entire crisis without having to rewrite the fundamental laws of physics.
Because if you're wondering why should even care about a slight discrepancy in some cosmic math, it's vital to remember that this isn't just about, abstract numbers on a chalkboard. This is about the age, the physical recipe, and really the ultimate fate of the universe. If our math here is wrong, it means our entire understanding of reality is just missing a crucial ingredient.
A missing ingredient in the recipe of reality. I love that. But to figure out what that ingredient might be, we have to establish the baseline of the crisis.
Yeah, we have to go back a bit.
We do. We know the universe is expanding. We've known that since, the 1920s, when Vesto Slipher first noticed the light from distant nebulae was stretching out.
Right, the redshift. And then Alexander Friedman crunched the math on general relativity.
Yeah, and George Lemaitre figured out the proportionality of it all, until Edwin Hubble finally proved it observationally in 1929. He showed that the farther away a galaxy is, the faster it's receding from us.
An observation that famously forced Albert Einstein to abandon his cosmological constant.
Oh yeah, his quote-unquote greatest mistake.
Exactly. He had inserted that mathematical fudge factor into his equations just to keep the universe static, because that was the assumption at the time.
Right, so the static universe is dead. We know it's expanding. The existential question now is just how fast. And that brings us to our cosmic speedometer, the Hubble constant.
Or H0. As it's written in the papers.
Right.
So the Hubble constant measures the current rate at which the actual fabric of space is stretching, and we measure it in kilometers per second per megaparsec.
Which is a bit of a mouthful. And a megaparsec is an almost unimaginable distance for us. We're talking roughly 3.26 million light years across.
That's vast.
So if the Hubble constant is, say, 70, that means a galaxy sitting 1 megaparsec away from us is receding at 70 kilometers every single second.
Yes.
And a galaxy 2 megaparsecs away is receding at 140 kilometers per second, simply because there's literally twice as much expanding space between us and them.
Exactly. It's a beautiful, elegant equation, really. Velocity essentially equals the constant times distance. But here is where we hit the Hubble Trouble.
The speeding ticket.
Right. When cosmologists try to measure this constant today, they rely on two primary methods, and they are completely deadlocked.
Okay, so in lane one, we have the late or local universe measurements. This is where we look at our relative cosmic neighborhood using what astronomers call standard candles.
Yeah, the sources specifically mention Type Ia supernovae and Cepheid variable stars.
Right, but to understand why this matters, we should probably look at how a standard candle actually works. I always think of it like a standard 100-watt light bulb.
That's a good analogy.
If you know its absolute true wattage, you know exactly how far away it is just by measuring how dim it appears from your front porch. Because, light fades at a very predictable rate over distance.
Exactly. So by finding these specific, predictable, exploding stars, these standard candle astronomers can calculate the local expansion rate, and they consistently get about 73 kilometers per second per megaparsec.
73. Okay, but in lane 2, we have the early universe measurements. And here, astronomers aren't looking at individual stars at all.
No, they're looking at the cosmic microwave background, the CMB.
The fossilized afterglow of the Big Bang itself, the universe's very first light.
Yes, but they don't just measure the CMB and stop there.
Right, they have to project it forward to today.
Precisely. They look at the dense, hot plasma of the early universe mapped out in the CMB, and they run the physics forward using the standard model of cosmology, which is known as the lambda CDM model.
Which basically assumes a universe governed by dark energy. That's the lambda part, and cold dark matter.
Right. So you take the starting conditions, you apply the rules of lambda CDM, and you calculate what the expansion rate should be today. And that calculation yields roughly 68 kilometers per second per megaparsec.
68. So we are right back to our radar gun problem. The CMB, at the start of the trip, clocks the universe at 68. The standard candles in the local universe clock it at 73.
Yep.
Does this mean the universe actually accelerated its expansion in some weird, unexpected way? Like, do we need new physics? Are we talking about exotic forces or, I don't know, dark energy that changes its strength over time or decaying dark matter?
Or are our local standard candles just flawed? And that right there is the dividing line in modern cosmology. For a long time, the assumption was simply that as our telescopes got more sophisticated, these two numbers would eventually converge.
They just meet in the middle.
Right, but they haven't. The measurements have only gotten more precise, which means the gap has persisted. The tension is actually stronger than ever.
But, I mean, relying on those exploding standard candles clearly has a blind spot, right? Because if the light from those 100-watt cosmic bulbs gets distorted, the math just fails.
Absolutely.
Like if there is intergalactic dust acting like a fog, or if the chemical makeup, the metallicity of the stars throws off their brightness even slightly, that 73 measurement is built on a house of cards.
Which is exactly why scientists realized they needed a totally independent third way to measure expansion in our local cosmic backyard. They couldn't just keep staring at the Big Bang, and they couldn't just keep looking at the brightness of distant supernovae.
And that leads us directly to the breakthrough research highlighted in your sources, specifically from astronomy and astrophysics. These researchers completely abandoned light-based distance measurements.
They did. They completely bypassed it.
They didn't look at the brightness of stars. They looked at the architectural dynamics, the raw physical behavior of local galaxy groups, specifically the Centaurus A and M81 groups.
What's fascinating here is that they utilized what essentially amounts to a cosmic tug-of-war method.
A tug of war.
Yeah. If you look at the extreme outer edges of these galaxy groups, you find these tiny dwarf galaxies that are caught in a massive clash between two opposing forces.
Okay, let's visualize this for a second. Think of a dwarf galaxy running on a treadmill. Pulling it forward, like inward toward the center of the galaxy group, is gravity. It's the mutual gravitational attraction of all the mass in that group trying to pull the dwarf galaxy in.
Right. The researchers call this the peculiar velocity.
Peculiar velocity. Okay, but the treadmill belt underneath the galaxy is pulling it backwards. That belt is the cosmic flow.
Yeah.
The Hubble flow itself, the raw expansion of space dragging the galaxy away.
That treadmill analogy is highly accurate because as you move further away from the dense center of the galaxy group, gravity gets weaker, obviously, but the amount of expanding space, the speed of the treadmill belt, gets stronger.
Because there's more space between them.
Exactly. So there is a very specific mathematical boundary line around these groups where those two forces perfectly cancel each other out. It is called the zero velocity surface.
Wait, so if they locate that exact boundary where the dwarf galaxy appears to stand perfectly still, where the inward pull of gravity perfectly matches the outward stretch of the universe, they can essentially reverse engineer the speed of the treadmill.
They can. They absolutely can. And what makes this method so incredibly robust is that it relies entirely on physical kinematics.
Just movement.
This velocity and distance geometry. It completely bypasses the systematic errors of the traditional distance ladder. You don't have to worry about cosmic dust dimming your supernovae or star metallicity throwing off your calibration.
Because you aren't measuring brightness at all.
Exactly. You are measuring the expansion of the space those galaxies are sitting in by watching how they physically move, not by how much light reaches our telescope.
It is an entirely independent check on the system. Like you are mathematically constraining both the mass of the galaxy group and the Hubble constant at the exact same time.
It is a brilliant piece of observational geometry, truly.
So we have this incredible new tug-of-war tool. What happens when scientists actually pointed at the Centaurus A and M81 groups? What does the readout on this new independent radar gun actually say?
Well,
Here's where it gets really interesting. The new data point for the local expansion rate isn't 73, and it isn't 68. The result is 64 kilometers per second per megaparsec.
a truly disruptive measurement.
I have to admit, I was genuinely confused when I hit this part of the research.
It's a bit of a head-scratcher.
Because 64 is lower than the local 73, and it is lower than the early universe 68. How on earth does introducing a third number, which is lower than both of the existing numbers, help solve a tension between a high number and a middle number?
Yeah, it feels like it just makes it worse.
It feels like dragging the anchor down to 64 just adds a third lane to the cosmic traffic jam.
It seems highly counterintuitive at first glance, but if we connect this to the bigger picture, a value of 64 actually softens the tension significantly because it breaks our confidence in the 73.
Because the entire crisis is built on the ironclad assumption that the local universe is definitely expanding at 73.
Exactly that. 73 was considered the undisputed anchor of the late universe camp. But this independent tug-of-war method comes along and says, the local universe is actually expanding at 64.
Wow.
That suggests the 73 standard derived from local supernovae might just be a massive systematic overestimation. Our primary local measuring stick was simply reading way too high.
So we had a dirty windshield when we were looking at those standard candles. And because 64 is much closer to the early universe's 68, it aligns significantly better with the standard lambda CDM model when you wind it forward from the Big Bang.
It completely changes the theoretical conversation. This finding strongly favors what cosmologists call a natural solution over an exotic solution.
And just to separate those two camps really quick, the exotic solution means the tension is real. It implies the universe is actually accelerating its expansion in ways we completely don't understand, which means we have to rewrite the fundamental laws of physics.
Right.
We'd have to invent new exotic forces to explain why the local universe is expanding so much faster than the early universe predicted.
Which, is a thrilling prospect for a theoretical physicist looking for a Nobel Prize, but it is incredibly messy for our actual understanding of reality.
Yeah, nobody wants to rewrite the textbooks if they don't have to.
Exactly. The natural solution, on the other hand, means the standard model of physics is perfectly fine. The universe isn't breaking its own rules. Our local radar guns just needed major recalibration.
Okay, that makes sense.
The 64 reading tells us that the universe is likely expanding at a much more consistent rate than the Hubble tension implied. The Hubble Trouble is probably just a lesson in measurement precision, not a fundamental breakdown of physics.
That is wild. The boring solution of just having a flawed, light-based measuring stick actually saves our entire foundational understanding of reality.
It really does.
But as we see so often in these deep dives into the cosmic weeds, solving one massive mystery usually accidentally uncovers another. The natural solution might save the standard laws of physics from being entirely rewritten, but the specific granular findings of this galaxy group study accidentally challenged another sacred cow of modern cosmology: dark matter.
Yes. And this is where the local architecture of these galaxy groups becomes incredibly important to understand.
The neighborhood architecture they mapped out in this study is just staggering to me. When they looked at the M81 group, they didn't just find a random, chaotic scattering of stars and gas. They found intense, geometric organization.
Very specific structure.
Yeah, the inner 1 million light-year region of the M81 group is entirely tilted at a 34-degree angle. And if you zoom out to 10 million light-years, that entire group perfectly aligns with a vast, sheet-like structure of galaxies that stretches all the way across the cosmic void to the Centaurus A group.
It is a highly structured environment, which tells us a lot about how it formed. And what's crucial for the dark matter question is how the mass is distributed within that structure. Yeah. Standard cosmic simulations, the algorithms we've relied on for decades to understand galaxy formation, they insist that galaxy groups of this size must be submerged in massive invisible dark matter halos.
Because without that massive dark matter halo, the standard models assume the galaxies would just fly apart. Right.
Yes. The assumption was always that you needed this vast amount of invisible gravitational glue to keep the outer edges of the group bound together against the sheer force of the universe's expansion.
But that's not what the tug-of-war data revealed about Centaurus A and M81.
It is not. They discovered that these groups are not dominated by a single massive galaxy sitting in the center of a giant dark matter halo. Instead, they are dominated by what the researchers call binary hearts.
Binary hearts. So Centaurus A pairs closely with the M83 galaxy.
Yeah.
And M81 pairs closely with M82. They operate in tandem.
Exactly. And when they calculated the actual mass required to create that zero-velocity surface, that exact balance point in the tug-of-war, they realized something shocking.
This is the crazy part.
The visible mass of these binary hearts, the stars, the dust, and the gas we can actually see, accounts for almost all of the necessary gravitational pull to explain the group's behavior.
Let me try to visualize this. It's like looking at a massive, complex suspension bridge. For decades, engineers have been looking at this bridge and assuming there must be a dense network of invisible underground cables holding it taut, because the visible pillars just don't look thick enough in the computer models.
Right.
But then a new team comes along, measures the exact tension of the wind pushing against the bridge, runs the math, and realizes, oh, wait, the visible steel pillars are actually entirely strong enough to handle the load on their own. We don't need all those invisible cables.
That is a highly effective way to look at it. By demonstrating that the visible matter explains the kinematics of Centaurus A and M81, we are essentially poking a sharp stick at the dark matter giant.
We really are.
It suggests that we might need significantly less dark matter at these galactic scales than previously assumed. Now, we aren't saying dark matter doesn't exist. It is still absolutely crucial for the formation of the universe as a whole. But the ratio of dark matter to normal matter in our local universe might be wildly lower than the universal average predicts.
Poking the dark matter giant. I mean, you go out to solve a math error with the expansion of the universe, and you accidentally suggest that the invisible gravitational anchor of the cosmos might be vastly overestimated in our neighborhood.
Just a Tuesday in astrophysics.
Right. It really just proves how deeply interconnected all these cosmological mysteries are. You pull on the Hubble thread, and the dark matter sweater starts to unravel.
It certainly guarantees that astrophysicists will not be running out of fundamental questions anytime soon.
So we've been on quite the journey today. We've seen how tracking a cosmic tug-of-war on the treadmill of expanding space might just fix our universal speedometer.
It's a huge step forward.
It points to a natural solution where our previous local measurements of 73 were just artificially inflated by standard candle errors, and the real number is closer to 64, which nicely aligns with the early universe predictions. And simultaneously, this exact same method is forcing us to question our fundamental assumptions about how much dark matter is actually holding our local neighborhood together. But where does the scientific community go from here? Because a sample size of just 2 galaxy groups feels a bit small for rewriting the cosmic rulebook.
It is an incredibly small sample size, and the researchers themselves are the very first to admit that. This is a highly promising lead, but it is not a closed case. The immediate next step is massive validation. We need to expand this tug-of-war analysis to a much wider, statistically significant volume of space.
And practically speaking, how are we going to capture that much data? I mean, measuring the peculiar velocities of tiny dwarf galaxies millions of light years away doesn't sound easy.
No, it requires immense precision, which is why the astronomical community is looking toward the 4-meter multi-object spectroscopic telescope, which is commonly referred to as FORMOST.
Right, the FORMOST facility. I remember reading about that in the sources.
Upcoming data releases from FORMOST are going to be a complete game changer. It is designed to capture high-resolution spectra of thousands of objects simultaneously.
Thousands?
Yes. This will allow researchers to apply this exact same tug-of-war analysis to dozens, perhaps hundreds, of distant galaxy groups all at once. We need to see if that 64 kilometers per second per megaparsec value consistently holds up across different regions of the universe.
And if it does?
If it does, the Hubble tension is effectively resolved as a calibration error. But if it doesn't, if other groups show wildly different expansion rates, the case for new physics roars right back to life.
So what does this all mean? We're standing on the precipice of either beautifully confirming our standard model of the universe or realizing we need to throw the whole physics textbook into a black hole.
Basically, yeah.
But I want to leave you with a final provocative thought to mull over on your own. It's something mentioned deep in our source texts, the local void hypothesis.
Ah, yes. This raises perhaps the most important, unsettling question about our place in the cosmos.
Think about it. If this tug-of-war data is absolutely correct, and our local cosmic neighborhood really is expanding at 64, which is significantly slower than the rest of the universe, what if we were simply living in a vast, uniquely low-density region of space?
It is a direct challenge to the cosmological principle itself, the foundational idea that the universe, on a grand scale, looks and behaves the same everywhere.
Exactly. We always assume our vantage point is perfectly average. It's the ultimate main character syndrome. But what if the universe isn't expanding uniformly at all? What if we are just looking out from a highly unusual, quiet pocket of the cosmos?
It's entirely possible.
Imagine living in a sleepy, slow-moving rural suburb where the speed limit is 30, and blindly assuming the traffic moves at that exact same speed in the center of the chaotic galactic city. If we are in a local void, there is simply less local matter pulling back on the expansion, or rather, the density contrast is skewing our entire perception of the Hubble flow.
It reminds us that our vantage point is not absolute. We are observers deeply embedded within the experiment, subject to the quirks of our local environment.
We are indeed. It completely shifts how we view our place in the universe. Thank you so much for bringing these incredible sources to the table and joining us on this deep dive into the universe's greatest mysteries.
It's been great.
It's been an absolute blast unpacking the architecture of reality with you. So the next time you get a speeding ticket on your morning commute, just remember, even the universe is having trouble agreeing on the math. Until next time.